So the comment is, isn't this just a form of dimensional understanding, like we use different combinations of features to get the results closest possible to using all features? Yeah, I have not heard about this term dimensional understanding, so I don't know. I just came across this approach of reducing vertical federated learning to a distributed optimization problem in the context of consensus, average consensus, or network consensus methods. Yeah, let me now move on, because I need to hand over then at 5 sharp to the guest speaker. So the next flavor, or one of the main flavors, which also has received a lot of attention recently, is clustered federated learning. So in clustered federated learning, we assume that the nodes of a federated learning network, they naturally form clusters. And one way to think about these clusters is that they are approximately IID. So all the nodes, like let's say one node here is a hospital, and the data set it has is its healthcare records. And some of the hospitals have very similar statistical distributions of their local data sets. For example, they're all hospitals from Finland. Let's say they have similar statistics. Or it could be all hospitals that are considered during the same period of time when everybody's just hit by a wave of influenza. So for some nodes, the statistics or the distribution of the local data sets is very similar. And then we say these form a cluster. And this can be formulated by a simple probabilistic model where you say all nodes in the same cluster, the local data sets are drawn IID from the same distribution. The problem is, in practice, you don't know which devices belong to the same cluster. You only observe small-sized local data sets, and you would need to find out which one belong to the same cluster. And yeah, here is mentioned some application domains. In healthcare, when you want to train personalized models for hospitals, or even on the individual level, you want to train the same model for patients that are similar, or same personal training advisor for persons that are similar to me. For example, I have a certain height, weight, body mass index, preference for sports activities. So maybe my smartphone-based training planner should take into account the measurements or the data collected by others that have similar physical properties than I have. So here we get this intrinsic cluster structure. And it turns out that GTV minimization is well suited also for clustered federated learning because, as we have discussed earlier, the solutions of GTV minimization, they tend to be clustered. So depending on how large you make alpha, the larger subsets of nodes will end up with model parameters that are approximately similar. And in particular, if you choose for these variation measures, for this measuring the difference between, if you measure the difference of model parameters at connected nodes using a norm, which is not our main choice. So in this course, we use as our main choice, we use the squared Euclidean norm here. But if you would use here the norm, then it turns out they are exactly identical over a large subset of nodes. And this was one of the recent topics of our very own research. So I cite here one of our recent journal papers that characterized this cluster structure. However, the cluster structure of GTVMin only depends on the local data sets and the network structure. So that's why I denote this cluster here by C hat instead of C. Because this C hat, that's what we get out of GTV minimization, might be different from this cluster in our clustering assumption. Because this clustering assumption is like an oracle-based information. Somebody tells you, yeah, these 3 data sets, these 3 nodes belong really to the same cluster, but the data they observe, these are noisy realizations of the distribution. And based on how lucky you are, you really see that they are identical distributed, or you're very unlucky and you just see one of these local data sets just by bad luck has a very different shape, this one realization. So there will be some estimation error involved. But how can we reduce this, minimize this estimation error? Yeah, we can use statistical tests. So we can try to test if one local data set is sampled from the same distribution as another local data set. I mean, I guess this is one of the mothers of statistical testing problems. You have two data sets and want to know, are they drawn from the same distribution? And I guess this is a well-studied, I'm sure this is a well-studied problem with a lot of results and methods, methods studied methods for finding out or testing if these two local data sets are derived from the same distribution. And if they are, so if this test results in, yes, they are from the same distribution, then we put an edge. We can then also use some measures of distance between probability distribution, like a KL divergence, to choose the edge weight. So using the KL divergence between the empirical distributions, because the actual distributions we typically don't know. Or we can use the gradients. So we can use the gradients of some deep neural network evaluated for a given model parameter. So you could interpret gradients also as a way to translate a local data set into a vector. And if these vectors are similar, you say, okay, there should be an edge with a large edge weight between these two nodes. Okay, in the interest of time, I will now